Well, hello, Nick the Vic here, M0NTV, and welcome back to my shack and to another M0NTV home brewing video. Now, I'm in the process of building a transceiver. I'm always in the process of building a transceiver. Life is one long process of building a transceiver. But at the moment, it's not a transceiver, it's a superhet. And I've been doing some work on RF amplifiers, and particularly in my IF stages. What I've tried to do is to do something that's as bi-directional as possible. In other words, instead of building loads of modules that will work for receive and then a load of fairly similar modules that will work on transmit, to build one module that will do both. And mainly for space saving as much as anything else, because those of you that know me know that I tend to build things in bigger and bigger enclosures. So I thought that would be good. Now, a little while ago, I came across a really brilliant article by Wes Hayward, no less, W7ZOI, and Bob Kopsky, K3NHI. And Wes and Bob, and you can get this article, I'll put the link down on Wes's website, designed a small signal RF amplifier. And there's two things that make this amplifier different to some of the other ones that I built. The first thing is it was bidirectional. So depending on where you fed your 12 volts would determine whether the signal would move through the amplifier from the left to the right or from the right to the left, which is really useful. Now the other really important thing about this amplifier is its termination insensitive, which means that it's buffered, so that actually what often happens with amplifiers is you might design them nominally for 50 ohms in and out, but actually if for some reason one port doesn't see 50 ohms, it can reflect that back on the other port then, so the input affects the output and all the rest of it, and actually that can be reflected back into previous stages of your radio then as well, so it's not a kind of good thing. But what they've done is they've created this amplifier, and it's just a few transistors, 2N3904, common transistors, that actually manages to do the process of an amplifier, but not to be dependent on seeing a good 50 ohms termination. In fact, you can pretty much have an open circuit on one end, and the other end will still see a good 50 ohms match. So it's really great, and where it's particularly good is for things like in IF stages where you connect into a crystal filter, and that can really mess up, even if you're trying to match it, with transformers, with what you're doing. So to be able to know that you can have a good 50 ohms match, irrespective of what the other port is seeing, can be a really useful thing. So anyway, I'll put the details down here, and we can have a little look at it. So this is the circuit itself. Now, in actual fact, what I'm going to be talking about is only half of this circuit, because I've built several of these now, but I actually wanted half of it. It doesn't need to be bidirectional today for my purposes, but it does need to be termination insensitive. So I just wanted the signal to flow from one to the other, but to have this insensitivity of the ports, which is a good thing. So this is the schematic, and in a moment you'll see my transcription of that, which will closely resemble how I'm actually physically going to build it. And that's really what I thought. I thought, well, very often I do videos about building, and I'll show people just the final product. But I thought it might be interesting to actually start from the beginning and show you how I physically do it, how I physically build it, how do I go about it, what is the board, how do I, and so so this is an intensely practical video that takes you stage by stage through the building of this design, and the testing afterwards, which is equally as important. So, without any further ado, I hope you enjoy. Well, welcome to the workshop and to the bench. And so I'm going to show you how I start off scratch building a project. Right, so here's our modified schematic.
And as I said before, we're only going to be building the top half of this amplifier. So what we're going to build it on? Well, what we're going to build it on is this stuff. So single-sided copper-clad FR4 it's called. It's about 1.5 millimeters thick, I think. And I tend to buy all mine in this. This is 100 millimeters by 70 because I find it's just a convenient size. You can stack modules, you can fit them more easily in enclosures with that kind of smaller size. I find you can get them in all different sizes. I buy them very cheaply. I get them in bulk from a famous auction website or Amazon. Now, actually, for this project we're doing today, because we're only going to, if we were building the whole thing, I would build it on one of these. But because we're only going to build half of it, the top half, what I did is I've actually cut one of these. You'll see, I cut one of these in half. So I used to use a hacksaw, but these days I just use a tenon saw, and that just gets right through it quickly. Then just sand the edges down so it's nice and smooth. And if you've got any bits that snap off, you might have to file those down, but that's okay. What's really important to do, depending on the quality of the board that you buy, and this stuff is not any great shakes really, but you will need to go over it with some fine wire wool is what I use. You can use sandpaper, but that really scratches the heck out of it. And that's basically just to remove any lacquer on there and make sure you've got a good conductive surface. And you test that, of course, by just putting the multimeter over it in continuity mode or even in resistive mode, and just see what the resistance is. Should be very, very low. Make sure that that's conductive over the surface, because you don't want to be soldering down a lead to the ground plane and it not to be a very good connection. So yeah, so you've got your board, and this is the board that we're going to use. Okay, and I'll show you what comes next. Okay, so the next stage is you get one of these. Well, any pen will do really. This is one of these old ones that was for writing on CD-ROMs. Remember those? And a Sharpie or something that'll do. And what I've done is the boxes over here, the kind of shaded boxes that you can see, and I said, remember, forget the bottom half, it's only the top half I'm doing. I've actually represented those by these boxes here, and it's better, and so you can see those. Yeah. Now, actually, I haven't done it perfectly for one important reason. This pad here that the 10k resistor goes to, actually I found, because I've built a few of these, is superfluous, and what you can actually do is take the lead there and connect it straight over to there. So I've done away with that box, but that's just through experience of having built this circuit a few times. So you've got that on there. So the next thing to do is to get engraving. Right, okay, so I've got one of these, well, it's like a cheap Dremel, really. Cheap Chinese Dremel, which I got from said famous auction website. Yeah, so all I'm going to do now, and they come with different attachments and heads. You can put this one Seen Better Days, but it does the job. So you're just going to go over this then with the Dremel, and I won't do that because I need too many hands, but I'll show you what it looks like in a moment. And you just go over and just take the copper off these marked areas, and that will give you your little islands, your little pads then that you're going to solder your components to. Right, okay, and here is the finished article. So what you'll need to do is you'll probably need to go over it at least twice, I find, because you do it roughly first, and then you go over it again and do it with a bit more precision. Then check it with a magnifying glass. Make sure there are no little stray bits of copper that are lying there that are going to short anything out. and then when you're happy with that, just clean it up because the dust gets everywhere. And incidentally, make sure you wear some eye protection, always wear goggles when you're doing this, because there's lots of bits of fine dust and copper you don't want flying around in your face. So safety first, folks. Yeah, clean it up, polish it up a bit, and then go over it thoroughly with a multimeter. I've just done that, and make sure that all these little pads are in fact electrically isolated from one another. And you've got one continuous ground plane then, and these little pads. And that is your board done. So that's great, and so we can go on to the next bit, which is actually putting the components on and building our amplifier. Now, just a word about the actual assembly. Depending on what your eyes are like, I actually use a pair of these now. I wear glasses. I've got some new glasses being made. Went to the opticians last week, but I find I need a bit more magnification. So these things are great, not very expensive. You can put different lenses in there, and they fit over your glasses if you wear glasses. And there's even a little light there, if I can do that. For if you're working later in the evening. So I find that quite a handy thing to use. Now, in terms of what we actually do and how we're going to do it, let me just try and get this focused. So you'll see I've tinned 2 of the pads there, and already, so a good fair-sized blob of solder on there. You don't need too much, but what we've got to do, of course, is we've got to take our components. So we've got to take our capacitor, which looks like that, of course, for instance, and you'll see the legs there. We've got to try and get that onto here. So how we do that is, let me just put this one on the board here and try and zoom in so you can see it, is we do this. So what I've done is I've bent those legs around, so I'm not sure you can see that very well, bent them down and splayed them out, and then chopped them off. And actually, if I can put this on here, hopefully you should be able to see that will just about perfectly fit onto there. And that's what I'm going to do. Now, how you do this, you can, depending on how asbestos your fingers are, you can kind of hold one bit. Don't hold the lead, because it will conduct the heat and it will get very hot very quickly. But you can kind of do that, hold it, and solder that lead in there. You probably can't see very easily what I'm doing. You can use the Julian eyelet trick, which is to get a blob of blue tack and anchor one end down and solder the other one. Obviously the end with the blue tack gets a bit hot and sticky, but once it cools it comes off fine. I've used that many times. Or you could use a pair of tweezers and hold it. The advantage of putting your solder on first with this is that you're not struggling trying to hold a component, hold your soldering iron, and holding the solder as well. It's just a question of melting that and letting the solder flow around it. So I'll do that and show you what it looks like. Okay, so I've done that one, and you can see there the solder is just, I'll put it down, hopefully I can get in there. The solder has just kind of flowed around it, and yeah, makes a decent job. Just be careful when you're doing this. You need to have in mind the distance. Make sure you're not shorting your leads to ground. And the good thing about using this kind of Dremel method is actually there's a very a big width of copperless border between each of my pads, which is great. So that will protect against some inaccuracies, but you've got to be careful with it. So now I'm not going to do this for every component, you'll be pleased to know. But I'll just do a resistor to ground so you can see how that goes, because you're going to be soldering a lot of things to ground as well. The good thing about this is, of course, that the pitch is the same, so they're the same height. So when you use do Manhattan style with the little me pads and things, Rex's me pads, which I often use, are very good. But you can have components of different heights. Then you kind of have to think about whether you have to make one leg longer than the other, or not. Maybe that's just me being OCD, probably. Right. Anyway, let's do a resistor. Right. Okay. So that's the first resistor put on here now. Let's just see if I can get this in focus. Okay. So you can see now. What I do is I cut the leads pretty short. Now resistors, you do need to be particularly careful with this construction technique that you don't short them to ground, mainly because resistors obviously lie flat, so you just need to be a bit careful with that. What I tend to do actually, now I did use the blue tack method for this. I put a blob of blue tack on there first and soldered the lead in on the pad, not particularly well, but that was all, just to hold it. Then I lifted the resistor up and put a blob of blue tack, put a blob of solder on the board, and then I tend to use like a small screwdriver just to apply a little bit of pressure onto the lead of the resistor, just to hold that down, not too much, as you use your iron on the end of it and get that get a good connection there. And then actually I went back with the same screwdriver and did the same, and actually I put a little bit more solder on there and just held that down and made a better connection there. So and that seemed to work pretty well. And if you're at all unsure about whether it's a good connection, just get the multimeter on it and do it all the way through if you have to. It's better to find those mistakes sooner rather than later. And that's pretty much it. You go through and you adopt the same thing. I'm going to go through now and build this, but I'll do another very short little video clip of me putting the transistor, a transistor in the 3 transistors, because that again is a little bit different. Okay, I have assembled all the other components apart from the transistors. Should just say as well, there's a couple of connecting bits you can just see there where you're linking the collectors actually that go to the ultimately to the 12-volt power supply. And actually what I use is I'll probably just show you over here. All these components, resistors mainly, and capacitors that we're using, I snip off the ends and keep these. Don't throw these away. I keep a little pot of these, and when it comes for to making these short connections with wire, they're great. So you can bend them. Now the other thing to be aware of is if you're using the Manhattan style with the pads that stand proud, you can of course put these connections flat and they'll lie flat. And there'll be a clearance between the top of the pad and the ground plane, which is great, which is just what you want. The problem with this, of course, is if you were to lie those connections flat, they would make contact with the ground plane and short out your power to ground. And I'm sad to say that was what happened the first time I started using this technique, which just, I suppose, goes to show that when you use a different method of construction, there are other techniques and things that you will need to employ. So it's not one size fits all. You'll discover these and what works best for you. But anyway, so that's all on there now. It will need some RF connectors and it will need the actual power supply lead. Of course, we'll do that last. But what I want to talk about now for a moment are the transistors. Okay, so we're using nice and simple 2N 3904 NPN transistors like these. Most important thing, first of all, is work out which lead is which. Now this might sound simple, but let me tell you, my number one mistake, even today in building circuits, I'm ashamed to say, is soldering in transistors the wrong way around. Because they may look very similar, but very often the arrangement of the leads is very different. So what I can tell you for the 2N3904, you'll see it's like a D shape here. D shape here like this. if you look at it side on. Put the flat face towards you with the actual the writing on it that says what it is, and from left to right you've got the emitter, the base and the collector. The emitter, the base and the collector. So what I do to actually mount them on, first thing I do is I hold it upside down and I splay out the leads so you can the legs so you can get at them basically. And then we're going to bend them down. So I bend them down like this. So I bend the base in one direction, which is the middle one, and the collector and the emitter in the other direction. And then we're going to make two more bends as well. And you're going to create some little feet. Kind of hard to explain and impossible to demonstrate whilst trying to hold this and hold the camera as well. But you'll end up with something that looks a little bit like this. Now I'll try and get this up so you can see this. So what we've got here, there, hope you can see that, are little feet. And you create this just by making some bends. Don't bend it too close to the transistor body or you'll snap the whole leg off. Been there and done that as well early on. And the point of doing this feat is you'll see it just gives you a bit more room to manoeuvre without shorting other things, and you know it makes a better job. So now hopefully what you can do is to place this on, and where it will go, I'll put it on and then I'll show you. It will go something a little bit like that. So you can see there how those leads will just fit into those little squares, and I'll solder those in. So I do this arrangement for every transistor, and then I'll solder them in, and then I'll show you what it looks like. Okay, well, we have the transistors on. So you can see that. So yeah, they went on okay. So there's only two more things to do actually. We just need to fix some RF connectors on, and because ultimately I'm going to be hardwiring this in, I'm just going to put some temporary RF connectors on. Sometimes I would just solder some chassis mount BNC connectors on. That's what I would usually do, but I'm just going to put some temporary ones on for now, and a power cable, and that's it. And so finally there it is. So as you can see, I've fitted the power cable for the 12-volt power supply, and a couple of just temporary BNC connectors on there so I can test it. And I've been over it with the multimeter again, continuity testing. Whenever you put leads on, really important to do that. So make sure that your power in is not being shorted to ground anywhere. Make sure you've got proper continuity of the centre pin of the BNC and the ground of the BNC to the appropriate places. And when you're satisfied that it looks good, or as good it's going to get, then it is done. And the next bit is the fun bit, because the next bit is the smoke test. Right, so I am back in the shack and at the bench in the shack, and okay, so here, ignore all this other stuff. This is a super het I'm building at the moment. So here's our module that we built, and we're going to give it the first, probably the most important test, the smoke test. So called because you put it on, you power it up, and you really hope that you don't get smoke coming out, because once that magic smoke is out, it ain't ever going to go back in again. So, are you ready? 3, 2, 1. Well, hallelujah. 31 milliamps, which is exactly what it should be. I've actually modelled this circuit in LT Spice, and that's what it should be. And really importantly, no smoke. So passed the first test. Okay, so I'm not sure how clear this will be, but we're going to test the amplifier now. So on the SIGGEN, you'll see just about I've got 50 millivolts peak to peak at 16 megahertz sine wave, because this amplifier will be used in my IF stage of this super het that I'm building up here, and the crystal filter I've built is for 16 megahertz, so that's what I'm going to try it out at. So that's what we've got. Now if I can scan down here to the oscilloscope, so I've got all these leads in the way here, hopefully you can see there, there's two cursor markers there, S and E, and you see I've got the S marker sat at the top of the signal. So that is the signal coming out of the SIGGEN. That's the 50 millivolts peak to peak. What we're going to do now is we're going to connect the amplifier up and see what a difference it makes. So remember, the S marker, the bottom marker, is the base level signal. Right, now I have connected up, coming in here, this comes from the signal generator, that same signal, that same base level 50 millivolts peak to peak sine wave at 16 megahertz going into the amplifier, and then coming out and going down here, down here, down here, down here, down, and into the oscilloscope. So I'm going to bring this up, and what we're watching here, of course, is the fast Fourier transform mode of the oscilloscope, and hopefully you can see here now, this is the gain of the amplifier. So I've got the E cursor, the top one, set to pretty much the top of our signal now, and if you look to the bottom left, bottom right hand corner, the bottom figure there, that is the difference in decibels between those two markers. So that's effectively the gain of our amplifier, and you'll see it's reading 15.2 dB, and that is right on spec for what Wes and Bob said this amplifier would produce with the original configuration. And so that is looking great. Okay, so this is the same test, but done with different instruments, just to prove that you can trust your measurements. So this is the tiny SA. So and hopefully you can see at the top there, the very top line, minus 28.8 dBm. So that's what the base 50 millivolts peak to peak is reading, and so now we're going to put the amplifier on it and see what difference it will make. And here is the tiny SA with the amplifier connected, and you'll see that the signal has now shot up to minus 14.3 dBm. And so if you calculate the difference between those two figures, the 28.8 and the 14.3, you get 14.5 dB difference, which is the gain, which is not a million miles away from the 15 dB that we calculated on the FFT function of the oscilloscope. So we're in the right ballpark there, and the amplifier seems to be working as we designed it.
And so there you have it. Job's a good one. Works really well. Now, of course, there's many other tests that we could have done, but I wanted to try. This video is getting longer and longer, so I wanted to try and keep it short. We could have tested for how linear the gain is across a frequency range, and had a graph showing you can do that. We could have tested the noise figure to see how much noise the amplifier is adding to our signal chain. Loads of other stuff you can do, but hopefully that will give you an idea about the kind of things that you can do. So I hope you found that of interest, and until next time, thank you very much for watching. Look after yourself. 73. Bye bye.